Hello. Thank you for tuning in and taking time from your day to participate in the latest in our series of CDSG webinars, Securing Next Generation Storage, Removability in a Solid State World. We have viewers today from all over the world, and I hope you and yours have been faring well as we collectively are in the various stages of adapting to COVID-19 and its impacts on our lives. My name is Chris Krull. I am the Director of Marketing here at the CRU Data Security Group, the parent company of the CRU Removable Storage brand. CRU has been entrusted to secure sensitive data for over 30 years with our removable storage devices. You'll find our products in the hands of well-known organizations and government agencies all around the world. Before I introduce our guest speaker, I'd like to cover a few housekeeping items. Everyone except our presenter will be muted throughout the session. You will have the opportunity to post questions throughout the webinar. You will find a question and answer section in the right-hand portion of your streaming window. We will address as many questions as we can at the end of the presentation. Also at the end of today's session, we'll announce our next CDSG webinar topic. And the last housekeeping item is to let you know that we will send out a survey after the webinar as we value and welcome your feedback. Today, we are pleased to have David Kaysen join us to discuss the considerations his team takes into account when developing robust removable storage solutions based on PCIe NVMe SSDs, including how to achieve high performance and meet and maintain PCIe compliance. As you know, PCIe NVMe SSDs are rapidly displacing SATA technologies, yet the need for storage removability for data security and transport is as high as ever. David is the Director of Engineering at CRU Data Security Group. He holds a degree in electrical engineering from the University of Illinois and holds 3 US patents. David has over 30 years of experience developing storage and PC solutions at Intel, Motorola, and Honeywell. He is an avid cyclist who enjoys road and mountain biking, as well as cyclocross racing. Without further ado, I'll turn it over to David.
Thanks, Chris, and thank you for everyone for joining for this topic. The topic today is optimizing systems for NVMe removable storage applications. So we'll move on to the agenda. There are 3 main areas that I'm going to cover. First, in introduction, and then signal integrity considerations. We'll go over what it takes to create a PCI Express margin success criteria, go over some of the certification considerations, critical system components, and I'm going to make an argument that it's a system, and this removable storage needs to be treated as such. We'll also go over thermal management topics and durability. So, introduction. As Chris mentioned, SATA-based storage media has stalled on the performance treadmill, and NVMe or PCI Express-based media has picked up that baton. Solid-state storage is closing the dollar per gigabyte gap, and thus NVMe media has become more prevalent in compute devices. So we see them regularly in shipping desktop PCs. The need for transporting and securing large data sets is a persistent requirement for government, defense, and industrial applications. And we're seeing here at CRU that DoD contracts are shifting requirements toward non-volatile memory. And finally, this intersection has presented system integrators with unique technical challenges that require system-level solutions. So I'd like to start out by illustrating a typical removable NVMe storage architecture. So on the left-hand side, the PCI Express bus will originate on some sort of motherboard and be connected to the CPU or the PCH on that motherboard. And those signals will be routed to a PCI Express connector or an M.2 slot. And one way to connect to those would be to plug in a host bus adapter card, HBA, or add-in card. And that card might have a retimer or a redriver chip on it in order to condition those signals, because we're going to be transmitting them across a cable. And the cable length may vary depending on the solution, but we're transmitting by 4 PCI Express across the cable, which also has connectors associated with it. Then on the right side, the cable connects up to the removable device, and it consists of several printed circuit boards that have routing on it. And you can see that the docking pair connector connects those two, and that is the connector that enables the removability. So we want a very high durability connector, and it also has to be capable of transmitting the PCI Express signals. And then finally, we have the NVMe connector that in this case, an M.2 SSD is plugged into. So the point here is that removability adds non-standard elements to the PCI Express channel that aren't covered in the PCI Express spec. So these cables, extra printed circuit boards, the connectors, even though they may be rated for PCI Express signal speeds, there isn't a budget for how these will impact the signals. So we'll get into more detail about that budget. And so we're going to go over this PCI Express success criteria case study. So the PCI Express channel budget is primarily made up of 2 elements: jitter budget and insertion loss budget. Jitter is how the differential signals behave over time. So as variables in the system change the timing of those 2 differential signals, that creates jitter. And insertion loss is essentially how the signal is attenuated by all of the elements in the channel, and therefore you're losing voltage essentially. So jitter is timing, insertion loss is voltage. The PCI Express compliance spec essentially consists of the PCI Express device, which on the motherboard could be a CPU, a PCH, or some other type of device. And then you'll have the motherboard portion of the budget, which will consist of the routing in that motherboard and the PCI Express connector itself. And then finally, you have an add-in card. So this is, as I showed in the previous picture, the host bus adapter that is going to connect our removable system. And in this budget, the removable and the SSD have to share the add-in card budget for both jitter and insertion loss. So let's walk through the 3 case studies here. So in the first case, the PCI Express device is the CPU, and it's hooked up to motherboard slot number 1, and it may have some margin, both jitter and insertion loss budget, compared to its budget. The removable takes up a certain amount of that budget, and then the SSD, in this case SSD number 1, takes up some of that budget as well. And in this case, they all stack up and create a passing condition. In case number 2, this is a different set of PCI Express lanes, and they originate from the PCH. And they're connected up to a different motherboard slot, number 2. Now, in this case, I've just illustrated that additional margin is available because the PCH and motherboard number 2 slot may have additional jitter budget and assertion loss budget that the other slot didn't have. In this case, the removable is the same, and SSD number 2 has a similar jitter and insertion loss as SSD number 1. And again, this case is compliant to the PCI Express jitter budget and insertion loss budget. Now in case number 3, we're using the same PCI Express slot as case number 2, the PCH and motherboard slot number 2. And again, the same removable. So the removable consumption of the add-in card budget remains the same, but now SSD number 3 has taken up a larger portion of the add-in card budget and has pushed the whole channel into a failing condition. Now, what are the consequences of not passing the PCI Express compliance spec? Well, we've noticed through experimentation that the read-write bandwidths will be limited. So the PCI Express Gen 3 speeds can be downgraded to PCI Express 1, Gen 1 speeds, and you'll see that in the performance that the SSD provides. So you get a degradation there. The channel can be non-functional. So sometimes the SSD can't even be seen by the host because the signaling doesn't even allow them to communicate. Or you can have an unreliable situation where under some conditions it does work, but then in others, when another variable is introduced, like maybe temperature, all of a sudden the PCI Express bus is not functional. So low bandwidth, totally non-functional, or unreliable operation could be some of the consequences if you're not passing PCI Express compliance. PCI Express compliance for removable NVMe systems. PCI Express compliance testing requires very specialized equipment. In this picture, I'm showing the PCI Express SIG compliance board that is used to test add-in cards. So we have found that the removable systems should be tested via the add-in card method. But unfortunately, no official PCI Express SIG M.2 compliance test board is defined in the spec, and there are some test boards that are on the market, but they're not recognized by the PCI Express SIG. So we recommend using each SSD that you're going to be qualifying in your system in the test setup. So the removable is tested as a system, an add-in card system, and therefore all of the variables such as the SSD models that you're planning to use, the different cabling solutions that you might use, maybe different lengths, and all of the potential add-in cards or connection mechanisms need to be tested for compliance. Now I want to illustrate some of the test results that we've gathered from some of these case studies. So these are the transmit I patterns from some testing that we've had performed. And the I pattern is a measure of both the loss and the jitter. So as jitter increases, you'll see the crossover points for the differential pair get essentially fuzzier because they're changing over time, and those crossing points are, again, moving with respect to time. And as insertion loss increases, you'll see the height of the I collapse. And again, that's voltage related. So again, as insertion loss increases, the I height collapses. So in these examples, SSD number 1 was used, and we have a healthy transmit I. And similarly for SSD sample number 2, actually the I was a little bit further open and actually was a little bit better. But with SSD number 3, that was the failing condition, you can see that the I is collapsed as far as the height is concerned. And also the jitter has increased because those crossing points have gotten fuzzier. And you see the little red triangle, and essentially that is the compliance I, and the blue signals have to stay away from that compliance I. Next are the receive tests, and the receive test is when the SSD is transmitting back to the host. And you can see here that the automated test procedure is run by the oscilloscope and the software infrastructure loaded into the oscilloscope. And these were the results for sample number 2. And you can see those blue dots are within the upper and lower limit and therefore are a passing condition. Now in the case with SSD sample number 3, the receive compliance test wouldn't even run. It was so far out of spec that the oscilloscope couldn't even run the test. So we had no specific data return that we could compare against the passing case. Now, there's another tool that we use for evaluation, and that's the Intel I/O margining tool, or IOMT. And this tool is provided by Intel, and what it essentially does, it controls their PCH or their CPU to change the margins of their device and performs a loopback test and essentially measures an eye diagram. And here again, in this case study, we have sample number 1 with healthy margins, and the way to interpret these plots are the gray area is essentially the eye that you want to stay out of, and in the left-hand case, the results did so, and therefore we're passing. But on the right, this is SSD sample number 3, and you can see that the data eye has collapsed into the gray, and therefore is an indication that this was not a healthy channel. Now, we don't use the Intel I/O margining tool as the ultimate compliance indicator. We use the actual PCI Express SIG method to guarantee compliance. We use the I/O margining tool as an indicator and something that we can run easily in our labs. Other considerations are when designing host bus adapter cards. So signal routing must be carefully done on these cards, matching your trace lengths of the differential pairs. And you can see in this example that we have, these differential pairs have been very closely length matched. You also want to limit layer transitions to not have too many vias going between layers. Those create impedance discontinuities that can create insertion loss and add jitter. Also, you notice that we're voiding ground planes around the signals, and that's to maintain the 85 ohm plus or minus 10% impedance that's required by PCI Express. Not only do you want to specify that 85 ohms plus or minus 10%, you want to verify that your PCB vendors are actually meeting those tolerances. So they can provide test reports from measuring the printed circuit boards and give you a report that they are indeed meeting your specifications. And then also, as I illustrated in the architecture, redriver chips can be deployed on the host bus adapter cards to boost the PCI Express lane signals and compensate for loss through the cables. Now, PCI Express redriver chips need to be tuned to optimize for the insertion loss margin of the channel that you're designing. And some of them can be optimized on the fly via software and be changed, or some of them are essentially tuned and then locked down with strapping resistors. For more complex transmission line topologies, retimer chips can be used, and retimers essentially recreate the PCI Express bus. They terminate it and then recreate it on the other side. So the host bus or the host, the PCH or CPU would be communicating with the retimer chip, and then the retimer chip recreates the bus on the other side to communicate with the SSD. Redriver chips are more like analog buffers, and they have adjustable equalization values that can be modified. But again, for more complex situations, you may want to use a retimer. They're a little bit more expensive, and that's why you may want to use a redriver if you can get away with it. Cables also have to be carefully considered. We happen to use Oculink connectors because they offer bandwidth for up to PCI Express Gen 4 speeds. And we also use high quality twin-ax conductors in our cables to ensure that we get reliable signal quality. And I have some pictures here illustrating the Oculink cable connection, and then also a diagram of the makeup of a quality twin-ax conductor. But even though you specify these materials, cables should also be thoroughly tested for the critical transmission specifications. So on the right-hand side of the slide, I'm showing some return loss test results for a cable, insertion loss, and again, an eye diagram that's going to be measuring both jitter and insertion loss. So as I mentioned before, this removable, it's a system in itself. And as demonstrated, individual components that are rated for PCI Express signal speeds and SSDs that are PCI Express compliant on their own may not result in a compliant system when put all together. Interchangeability of these components is limited by the lack of standards for removable memory solutions. The PCI Express SIG just did not think about removable memory when it came up with its specifications. It's a specialized type of application, and even in the NVMe extensions to PCI Express, there have been no provisions put in those specifications for this type of architecture. So system integrators must tightly control all the elements that make up the PCI Express channel to ensure compliance, and like I said before, making sure that you're getting the maximum bandwidth out of the channel, making sure that the channel is indeed functional, and that you're getting reliable operation. And finally, integrators must perform rigorous compliance testing on all the variable components to ensure reliable performance. So if you have different cable vendors or different cable lengths, different add-in cards that you may be using in your system, all of those should be tested in order to ensure compliance and reliable operation. So now let's shift gears a little bit and talk about another topic that's important, and that's thermal management. So NVMe offers us great performance, but that comes at a cost, heat. These illustrations that I've provided here show the heat generated by SSDs under different workloads. The top case is a light workload, and you can see by our thermal imaging here that the card is heating up just above ambient temperature, which would likely be 25 degrees. But in the bottom diagram, we're running a very heavy workload, and the card has heated up to which is right around the self-throttling point. Typically, we see in the specifications of SSDs that between 70 and 85 degrees is where the module will start throttling itself and limit the bandwidth. So thermal management is needed to prevent the SSDs from self-throttling, so you get your full bandwidth. Now, we do have that safety mechanism built in, which is nice, but we want to use fans, airflow, and temperature monitoring in order to mitigate the rise in temperature of your SSD. Now, some ways that you can approach this are airflow and thermal analysis. So system integrators need to optimize the airflow across the NVMe modules to prevent them from reaching the thermal self-throttling point, as I mentioned. And in the upper right-hand corner, you see the results of an airflow simulation that took into account the cooling fans and the airflow that is being routed through these vents in the front cover and across the modules, providing some heat dissipation to keep them cool. Selecting fans, designing the air ducts, and controlling the fan speeds are part of the system design process. And performing thermal analysis can aid in optimizing the design before you actually prototype it and get into a test mode. So the diagram on the lower right-hand side shows the results of a thermal simulation that was done. And you can see in there that some of the memory chips are getting a little bit hotter than others, shown by darker orange. And again, this can be done in order to aid the design and optimize it before you actually spend the money to build it and tool it up. But also, we have to optimize thermal transfer. M.2 NVMe SSDs are not normally provided with heat sinks. Now, there are some on the market that you can buy that have an integrated heat sink, but typically, most OEMs are buying them in their bare form. To transfer heat from the SSD ICs and to the heatsink, a thermal interface material can be used. And in these diagrams, I'm showing the thermal interface material. It can be thermal grease or various elastomer materials. And it is applied on top of the ICs and then couples to the heatsink. But the heat sinks and thermal interface material must be carefully designed and assembled to achieve reliable performance. So the bond line thickness of the TIM is very important to achieve optimal performance. And then as you're assembling the modules into these heatsink assemblies and module type of designs, you want to make sure that no debris gets introduced onto the thermal interface material, because that will degrade its performance. And then fan performance and control is also very important in the system. Fan performance must be carefully selected to meet the cooling needs. And in the lower left-hand side, I have an example of a fan performance curve, which illustrates the flow rate, or cubic feet per meter, CFM, over the static pressure of air that it's creating. Other things that should be considered are fan control to meet other requirements such as system acoustics. Some systems come with acoustic limits. Fans can be very loud, and when they're not needed, they should be turned down to lower speed so they make less noise. And I've showed two examples of control mechanisms that might be used. In the top right-hand corner, I'm showing a more gradual fan speed increase that's done in a linear fashion. So once a ambient temperature is reached, the controller would turn on the fan and then start ramping it up, its speed up to the maximum as the temperature increases. And in this case, you would have a temperature sensor that your microcontroller is reading in order to monitor the temperature of the devices. And then in the lower right-hand side is a different scheme that's much simpler. This is a high-low type of scheme where the fan might default to a slow speed of 3,000 RPM that would be barely detectable from an audible standpoint. And then once the temperature of the module reaches a certain point, in this case 55 degrees, the fan would be turned to its high speed, in this case 8,000 degrees, or I'm sorry, RPM. So these are different schemes that one might employ in controlling the fan, the cooling fans, in order to meet both the temperature requirements of the modules and the acoustic requirements of the system. The final topic is durability. And for removable systems and removable storage applications, connector durability is critical. And this is something that CRU has a long legacy of providing to our customers for, as Chris mentioned, over 30 years. And if you consider an application where you might go through 10 cycles of removing the media and replacing it for 5 years, this amounts to just under 20,000 mate and demate cycles. Now, a standard M.2 module connector depicted up in the upper right-hand corner, they're only rated for less than 100 cycles. So, but plugging into this standard M.2 module connector is not a good idea for removability. But then high-speed signal-rated board-to-board connectors that are good for PCI Express signaling speeds still are rated for less than 1,000 cycles. And I've showed an example of a typical board-to-board connector that is rated from the vendor for, again, just under 1,000 cycles. But again, that may not meet the application where we want to be up in the 20,000 cycle type of figure. So how do you go about extending the life of these connectors? Well, you have to design in durability. Mating connector life can be extended through system design. By controlling the mating position with guide rails and alignment features, the connector experiences less mechanical stress. And that typically will be on the plastic body of the two mating halves. Those can wear out and thus reduce the reliability of the connector. And also the contacts themselves can be damaged by misalignment. Also, unique insertion and extraction mechanisms can control the mate and demate force to preserve the contact integrity. So in the example that I show on the right here, we've designed in guide rails and alignment features to guide this module to mate with the printed circuit boards in the assembly in order to limit the play as it's inserted. And then the other mechanism, these levered extractor doors, were designed to gently extract the module by prying it out in a very repeatable fashion, and then also inserting it such that the insertion force is not exceeding and also is very consistent. But as they say, the proof is in the pudding. So durability testing must be done. And I'm showing a fixture here that we call Thumper. And this is the type of fixture that we use to measure mate and demate cycle requirements, and to guarantee that we meet the specifications that we place on our products and that our customers require. We do this type of testing all the time. Automated fixtures are the best way to perform this cycle testing with repeatable results. So we can control the insertion force, the extraction force, and get very consistent forces applied as we're performing this test. And then we also don't get a lawsuit from our technicians in giving them carpal tunnel syndrome. So in conclusion, designing high-speed NVMe removable storage into a system requires very careful consideration of PCI Express signal integrity, thermal management, and connector durability. And we know that complex system integration is hard enough as it is. So rely on the removable storage experts such as CRU to provide the removable storage for your application. We've done the work and will continue to do it for you. So with that, we'll open the floor to questions.
Great. Okay. Here's an opportunity. We just have a little bit of time left. Opportunity to submit some questions. We have had some come in. And I first want to thank David for sharing his view of the challenges when trying to apply removable drive requirements to NVMe technology, which, quite honestly was developed without really taking into account removability as a design consideration. I've watched the team work through these issues, and I know that, coming to these solutions is a non-trivial set of tasks. So let's take a look at some of these questions. There's a couple of folks who have asked about hot swapping NVMe. So clearly they're used to hot swapping their SATA-based removables. So can you address that requirement?
Yes, and what I can say is we're working on it. Yeah, the PCI Express bus is much less friendly to hot swapping, and therefore, again, requires a very highly integrated system solution. So Intel themselves have some solutions, mostly in the server space. They didn't envision implementing hot swapping in the desktop space because NVMe is typically a static, non-removable type of media in that space. However, we're working on solutions with add-in cards that have PCI Express switches that will enable the hot swapping, because we're going to be controlling that end of the bus. We're currently working on a design. We're also working with some OEMs and integrators on some solutions with our prior product, the QX310. So it's possible to do, but it's very tricky, and again requires a interaction from the host and thus the BIOS with the removable. And right now, our current solution on the market doesn't support hot swapping, but again, we're working on enabling that in the future. And even though this won't be a topic for the next webinar, once we get our solutions engineered and tried out, it may be a future topic for a webinar.
Sure. Well, speaking of future webinar, we've had a question come in that is a sort of a teaser lead-in to addressing some of the exact solutions that we've developed and are bringing to market. One of which is, do you have a list of tested and approved NVMe SSDs? And again, it might be a better addressed next time because we have a different approach here. But if you want to just tease that out, that would be great.
Yes. So we've tested our components, our system, with certain SSDs and SSD models, and we share that with our customers in order to guide them to a PCI Express compliant solution. Now, as I mentioned in the presentation, an OEM or system integrator could take our system and perform compliance testing on a different module that perhaps we haven't tested. In the future, we're planning to qualify certain media types and offer fully populated modules so that we've eliminated the need for integrators to go through that testing. So we will guarantee a fully compliant system by virtue of controlling all of the elements from end to end.
Yeah, I think spoiler alert, one of the differences you're going to see from us is that we'll be offering fully integrated, fully populated storage modules themselves. Are there any considerations as you work through these challenges between Gen 3 and Gen 4 qualification? I think you mentioned that, yes. Is this a Gen 4 solution? Is it backwards compatible? Can you address
Yes.
the whole Gen 3, Gen 4?
Well, we are designing our new chips platform with Gen 4 speeds in mind. So, for example, we've selected that Oculink cable type because of its characteristics. And we have done some preliminary Gen 4 testing with some positive results, but we're still engineering that and getting that ready for market. We do understand that some media, Gen 4 media, is starting to trickle out into the marketplace. Although I think some of the motherboard manufacturers and chipset manufacturers are a little slow to roll this out. So we're working on it, and systems that meet the Gen 4 compliance will be backwards compatible with Gen 3. Okay, great. Well, we have overstayed our welcome here. So again, that's what we have time for. I see we have a couple of questions trickling in. Which connectors have you had success with to achieve high durability cycle count? I don't know how much we share about the actual components that we design into the systems. So you have an answer there. Yes, and again, teaser alert, with our ships platform that we've just launched, we are providing the mating connector specification so that we can enable custom form factors to be used. So typically, CRU provides the docking stations that are integrated into larger systems. But we realize for some applications like handheld applications, perhaps notebooks,
Right.
or forward tactical type devices, that a NVMe module, removable NVMe module, might want to be designed into those devices. So we're going to be providing a specification, or we are providing a specification on how to integrate our module into custom systems, which does include the connector specification.
Okay, and I'll squeeze one last question in here. There's a question around time frame. So what is our time frame for availability of these fully integrated, fully populated solutions? This year, next year, if you want to give some guidance around that.
Well, sure. So today we have the QX310 on the market, and it's a single M.2 removable. And we do have a populated SKU available for that, and it's again fully PCI Express compliant. And then we've just launched the SHIPS platform, which the first docking station that we've brought to market is the QX448. It houses 4 NVMe modules in a new module form factor, and again, it's we've just launched the product. Development kits are available for purchase, and as soon as we start getting interest from customers, we'll be quoting lead times.
Okay, great. Thank you. Thank you so much. And thanks to those who have asked questions. You have an opportunity to engage with our sales team, with Dave, and pursue other topics as well. So as I mentioned, we'll be hosting a follow-on webinar that will dive a little bit deeper into some of the details around our specific solutions for this recently introduced SHIPS platform. We are tentatively scheduled to have that webinar on Tuesday, July 14th. So stay tuned. Everybody who attended or registered here will receive an invite, and we'll be promoting the webinar via our usual sales and marketing channels. So once again, thank you for your time, and be well.